Hi guys, welcome. We're looking at Math 7, Day 6. Thank you for being here, and we will go ahead and get into it. So we're doing lesson 41, 42, and 43 today, and still working without calculators. I know it's a little bit more time consuming, but it's just good practice. It's good foundational knowledge, and it'll make life easier if we're ever without a calculator. But down the road, when we start to use calculators, it'll just be a tool that we use, not something that we absolutely rely on. So lesson 41, okay, we're using formulas and the distributive property. Okay. So a formula, we've worked with those primitive formulas, area formulas, volume, different things like that. That is just a formula. So for this one, if we're looking at a rectangle, capital A is for area, and then L and W, length and width. So the area of a rectangle is length times width. We know that. And so if we're given an example here, okay, well, length is 8, the width is 4. We're going to plug those numbers into our formula. Okay. Here we have two variables. We plug them both in. 8 times 4 is 32, and feet times feet is feet squared. So that's why area is always square units, in this case, feet. So the area would be 32 square feet. We could draw out a rectangle and do all that, or we could plug it into our formula and solve for it pretty simply. Okay, so we've used formulas all before. Pretty simple, nothing new there. If we're looking at, notice the effects of the units when calculation is performed. Multiplying two units of lengths results in a unit area. So let's look at evaluate or solve 2 times L plus W when L is 8 and W is 4 centimeters. Okay, so length plus width, 8 plus 4 is 12. 2 times 12 is 24 centimeters. So in our rectangle, we can say 8 plus 8 is 16. 4 plus 4 is 8. 16 plus 8 is 24. We can just add them all together, or since we know in a rectangle, not a circle. In a rectangle, opposite sides are the same length. So, okay, length and width up here. Okay, these two sides would be the same measurement. We know these are all right angles. These opposite sides would be the same. So we can add up all four sides, or since we know two sides are the same, we can say, well, if we add up our two sides here and then just multiply by 2, that would represent these other two sides. So it's the same thing. It's just we can do it this way. If that's easier for us, add up length and width and then multiply by 2, and that would give us our perimeter, or we can just add up all four sides. It's the same calculation that we're doing. So that's all that is showing in this example. Okay, now the distributive property, when we look at these, oops, sorry, let me get to the right. Okay, the distributive property that we have right here, okay, if we distribute these into our numbers, okay, then we get 2 times the length plus 2 times the width. Okay, same thing we do. So we know in our order of operations that we perform whatever's in the parentheses first, okay, but it may be that one of these is an unknown or both of them are unknown. We can also distribute whatever is outside of here into both, or if it's 3, 4, however many terms inside our parentheses, all of those in there, then we would have to multiply by all of the terms inside our parentheses. In this case, it's a binomial. We have 2 terms. We multiply the 2 outside here by both of these terms in here. So we could distribute whatever's outside the parentheses inside our parentheses. Okay, if we want to do it using variables, and I think this is on one of your reference sheets, the distributive property, it may use, I think it uses ABC, but Okay, we have A times parentheses B plus C, so we could add B plus C and then multiply it by A, or that's going to give us the same thing as distributing the A into our terms inside the parentheses. So A times B becomes AB. Okay, plus pay attention to this sign. A times positive C is AC. So we have AB plus AC. So let's just look at our own example. Let's do 2 times 7 minus 3. Well, 7 minus 3, if we follow our order of operations, okay, 7 minus 3 is 4. 2 times 4 is 8. Okay, pretty simple. Again, there's no unknowns in here, so the distribution property probably would make it a little bit longer. We'd still get the same thing. So let's check it out. Let's see if we get the same thing. So we got 8 just doing parentheses and then multiplying, which again is correct, but we'll use the distribution property usually when we have an unknown in here. Let's just prove it to make sure that it is correct. So we distribute 2 times 7 is 14. 2 times negative 3 is negative 6. 14 minus 6 is still 8. Okay, so it's correct both ways. We can do it either way. Now, again, for this example, it'd probably be easier just to do 7 minus 3, then multiply it by 2. I agree. But this is just showing what the distributive property is and that it works out to be the same. So even though it feels like, well, we always do parentheses first, but if we have, say we're solving for an unknown, we have something like this. Well, what's x plus 5? We don't know because we don't know what x is, but we can distribute and get rid of our parentheses and call it x squared plus 5x. Okay, so that's probably more when we'll use it, when we're trying to get rid of parentheses and trying to solve for a variable or an unknown, and we need to get rid of the parentheses. We could do it by distribution. Okay, there's another example there if you want to look at it. Again, some of the different terms, the distributive, commutative, and associative properties we've talked about in the past. Basically, that just means that we can add in any order. Okay, again, 6 plus 4 and 4 plus 6 is the same thing. So that's just the associative and the commutative properties. Okay. Lesson 42, we're looking at repeating decimals. So again, we've talked about this. A lot of our decimals end up terminating. Okay? So they can terminate and end off where we have no more remainders, quote unquote, or we don't have to keep dividing. They can continue on infinitely with a repeating pattern, which those are the ones we'll be looking at today, or they can be irrational, in which case they go on forever. So we don't have any way to indicate. In that case, like pi, we would round it off to 3.14 or whatever we're looking at. So oftentimes they terminate. Either they're going to repeat or they're going to go on for forever without any sort of repetition. So let's look at some examples, or let's look at this term. So the repeating digits, it's oftentimes it's just one digit, one number that's repeating, or sometimes it's 2, it can be 3, it can be however many. The digits, the numbers of the decimal that are repeating are called the repetend. So it's the ones that are repeating. And to indicate that, we put a little bar above whatever numbers are repeating when they start repeating. So for this example, 0.31818181818, it's going to continue on forever. It's 1/8 that's repeating forever, not the 3. It's the 1 and the 8, not 8/1. It's 1/8. So we put the bar over the 1 and the 8. In this example, the 6 is repeating forever, so we put the bar over just the 6. Put it over one digit in this number. We put it over 2 digits in 2 digits in this example. So it just depends on when it starts repeating and what number or numbers are repeating is where we put the bar. And there's no way to put that in a calculator. We're not using calculators right now, but again, that's where rounding comes in, because we'd either want to express it with the bar above it or as a fraction, or we'd have to, if we're putting it into some sort of calculation, we'd have to round it because there's no way to put it in infinitely into the calculator. I think our calculators cut off at 9 or 10 decimal places. So let's look at example C. If we have all of these 0.083333. So the 3 is repeating, so we put the bar just above the 3. In this one, we have 5.142857, 142857114. I know it's hard to see all those. It looks random, but if we start looking at the 1428557, 1428557, and then it would continue on. So it's all of those numbers that are repeating. So we put the bar above all of those numbers. So again, it's usually 1 or 2 numbers that are repeating, but it could be 5, 6, 7, whatever decimal places that are repeating. It just depends on what we're looking at. Now, a question will probably come up down the road. I may even mention it here. These are still rational numbers, even though the decimal goes on repeating infinitely. Because it's repeating, we could express it as a fraction, so it would be rational. Irrational numbers like pi or square root of 2, square root of 3, things like that, they go on forever, but they never repeat. Then 454.5454545, it's the 5 and the 4, but we don't put it here because obviously that's not repeating forever. It's the decimal place that's repeating forever. If we're looking at these and we want to round to 5 decimal places, so we have 5.316, 5.316, I believe it was the 6 that was repeating. Yeah, it was the 6 that's repeating. Okay, so rounding this to 5 decimal places, again, we would just take it out to 5 decimal places. We already have it to 1, 2, 3. The 6 is repeating, so we're going to go 1, 2, 3, 4, 5. We'll go ahead and take it out to 6 decimal places because we always want to take it out to 5 decimal places. That means we need to look at the value to the right, the 6th decimal place. And if it's 5, 6, 7, 8, 9, we round up. If it's 0, 1, 2, 3, 4, we round down. So it's a 6, which means we round up, so to 5 decimal places. 1, 2, 3, 4, 5. And a lot of times in our calculator, when we do, like, if you do 2 divided by 3, it's going to say 0.6666667. That's rounding it for you at whatever 9 or 10 decimal places that it takes it out to. It doesn't mean that it's a terminating decimal right there. It's just, again, our calculators doesn't have any way to produce something infinitely. And there may be, I've never found anywhere to do the bar above it to indicate a repeating decimal. I don't think it's in there, so it just rounds for us. So in this case, we rounded to 5 decimal places. So again, we can write it rounded. We could express as a fraction, or we could put the bar over it, indicating that it goes on forever. So if we put it as 5.316 in our calculator, okay, that is close to this number, but it's not the same thing. So just be aware, like 0.3 repeating forever and 0.3, those do not equal each other. So they're very close. They look the same, but they're not exactly the same. Okay. So we just looked at that example, actually 0.3 and 0.333. Well, this one's going to be 0.3000 forever. This one's going to be 0.33333 forever. So this one would be greater than this one. Then if we have 0.6 repeating forever, 0.6 and 0.65, and we want to arrange those from largest to smallest, how we're going to do that? Okay, so let's first 0.6 repeating forever, and then I think it's 0.65. We want to arrange these from smallest to largest. So the first thing we want to do is, let's just take it out. We have 1 and then 2 decimal places. So let's just take it out to 3 decimal places. We could take it out to 4 or 5, however many we want. So 0.6 we can rewrite as 0.600. That's the same thing. We normally wouldn't write this, but in comparison, we're going to do that 0.666, and it's repeating forever, but we take it out to 3 and then 0.650. So now that we have it, we can compare place values. So the tenths place 666, that doesn't help us. The tenths place 0, 6, 5. Okay, well, 0 is the smallest, okay, then 5, then 6. So we take it out to more decimal places, then it's easier to compare. So 0.6 would be the smallest, 0.65 would be in the middle, and then 0.6 repeating forever would be the largest. Again, all close, all next to each other on the number line, very, very close, but not exactly the same numbers. And that would be the order that we would put them in. And if we were to do some of this in our calculator, again, certain number of digits display, we can see when they start repeating. Again, we won't have the bar in our calculator, so we'll just need to kind of look for that pattern. Okay, is it repeating? Is it 1, 2, 3, 4, however many digits are repeating, and go from there. If it can be expressed as a fraction, so like 1/7 is a fraction, it's a rational number, then it's either going to terminate or repeat. It's not going to go on forever. It's in fraction form. It's not some sort of complex fraction or something like that, then or irrational number in the numerator or denominator, then it will be either terminating or repeating. We may just have to take it out to several decimal places. All right, and this one, lesson 43, decimals to fractions, fractions to decimals, and percents to decimals. You guys will get very comfortable with fractions, decimals, and percents. Most tests usually have a table where you have given one and you have to find the other two. So you'll get very, very comfortable with converting all of these. So let's take a look at 0.125 as a fraction. Okay, well, we could put this, we know this is the tenths, hundreds, thousands, so we could put this 125 over 1,000 and do the division or factor out numbers, and it would reduce down to 1/8. Okay, so that's where knowing greatest common factors or down the road is you could use your prime factorization or what you know about numbers that end in 5 and 0 to start to reduce that down. But that would be 1/8. Now let's look at Mathia Road. Her bike, 11.45 miles to the lake. Write it as a mixed number. Okay. 11.45. Well, we're going to do 11, and well, this is tenths, hundreds, so this would be 45 hundredths. That's how we read it in decimal form. So we can immediately put 45 over 100. It's 45 hundredths. But then we will want to look and see, is there anything we can factor out? I know ends in 5, ends in 0, so I know 5 goes into both of these. So 9, and then 5 times 20 is 100, so 9/20ths. And nothing else we can reduce out of that, so 11 and 9/20ths. And if I was expressing this number and trying to tell someone a distance, I would probably use a decimal, but just for practice sake, we can write it as 9/20ths. So just remember, again, tenths, hundredths, thousands, 10,000s, 100,000s, and so on. If we have a decimal number, we can just write it instantly over 10 or 100 or 1,000 or 10,000 or whatever it is, and then we'll probably need to reduce from there. And it's 11 and a number less than 1, 11 and a number less than 1. Those are equivalent. Okay, so we'll write each of these as a decimal number. So 23 hundredths. Okay, that one would be pretty simple. 23 over 100. Well, 23 hundredths is 0.23 because that's 2300. So when it's over 10, 100,000, whatever, that makes it pretty easy because then you just have to figure out what your decimal point is. Next one was 7/4. So 7/4, 4 goes into 7 one time. 3 left over, 3/4. Again, I can multiply top and bottom by 25. That would give me 75 hundredths. So 1.75. Or these fractional parts, you can multiply it by a number to make it over 10 or 100 or 1,000 or whatever. Another thing you can do, 3/4. That may be one you know off the top of your head. Oh, I know it's 0.75. Or we can say, well, 3 divided by 4. 4 doesn't go into 3, but it goes into 37 times, which is 28, which gives me 2 left over. Add a 0, drop down. 4 goes into 25 times exactly. So I have no remainder, so 0.75. Three and 4/5. Again, 3 point and then 4/5. I would multiply top and bottom by 10, which would give me 8/10. So 3 and 8/10 or 3.8. 2/3, that would actually be a repeating decimal. So 2/3 or 2 divided by 3. 3 does not go into 2, but it does go into 20. 6 times. 6 times 3 is 18, which leaves me with 2 left over. Drop down to 0. 6 times 3 is 18, with 2 left over. Drop down to 0. Aha, it's going to be that same 2 left over all the time. So I know that it's going to repeat that same way over and over. So once I see that pattern, I can just write it as a decimal with the bar over it. It's just one repeating number, so I just put the bar over that one number. Percents, when we're converting percents to decimals or decimals to percents, I personally think that that's the easiest because I'll just show you a quick trick. Again, fractions sometimes are a little bit trickier. We still do them, no problem, but decimals and percents are, in my opinion, the easiest. So let's look at some of these. Let's look at 25%. So if I have 25%, again, I know that's 25% means per 100, so I could write that as 25 over 100 and reduce it down to give me my fraction, okay, which again isn't overly difficult, but converting it to a decimal is even easier. So 25%, okay, or we could call this 25.0. There's always a decimal there, even if we don't write it in, we know it would be there if we wanted it to. And then to convert it to a decimal, I'm dividing by 100, or since I'm dividing by 100, there's 2 zeros. That means I'm moving the decimal 2 places and I'm dividing, so to the left. So percent to decimal, all I got to do is I take this decimal and I go 1, 2 places to the left. 25% as a decimal is just 0.25. Again, I could convert to 1/4, do 1 divided by 4, give me 0.25, or I can just move that decimal 2 places to the left. Same thing if I'm converting. Let's look at one of these examples. Okay, they're all percents to decimals, but let's say we had, let's say we had 0.025, and we wanted this to be a percent. Well, we would multiply by 100, or we would move the decimal 2 places to the right. So I would take 0.025 and I would move it 2 places. 1, 2. So it'd be 2.5%. Okay, so you can do the multiplication and the division, multiply by 100 to move it to percent, divide it by 100 to move it to a decimal, or you can just remember I'm moving 2 places to the right or the left every time, and that makes it a lot easier. So a lot of times before you even write it out or have to do any math, a lot of times I'll just automatically move it. If I say, if I'm getting, someone's getting a 5% raise, okay, well, that's 0.05 is a decimal because we just move it over 1, 2 places. And if we have any blank spaces, we fill in a 0. So that's how we get that. So don't convert this to 0.5 because that would be 50%, not 0.05. If we want to move it back to a percent, times 100, 1, 2 to the right, okay, it becomes 5 or 5.0 if we want to write it with the decimal. Okay, so that is how we do those. In some, I don't think TI-84 has percents. I think there's a way to do percents. Obviously, it's fraction or decimals, but as we'll show you down the road, the easiest way, especially in a calculator, is just to convert it to a decimal. So in looking at all of those, we just move the decimal place. If we're going from percent to decimal, we move it 2 places to the left, so 0.25. 125 becomes 1.25. 2.5 becomes 0.025, and so on. 2.5 would be 7.5%, so we move it 2 places to the left. 300, 2 places to the left. If we want to work back to percents, then we move it 2 places to the right. So I think that one's the easiest just because we're moving a decimal 2 places right or left, and we're done. It's the same thing every single time. Okay, we're just doing 43 today, so that's all we have. We should have had a review that we went over. If you guys still have continued questions on that, come into Math Lab or ask them during class, and we'll try and get you guys squared away before you go in to take the test. But that is all we have for today. Thank you.